Hello, everybody. Today we're going to talk about analysis of variance, better known as ANOVA. So I want to get right to the point. When you're running ANOVA, utilizing Excel, it's really easy. But I still want to go through our basic steps of hypothesis testing because ANOVA to me is just another version of a hypothesis test. Let me show you why that's true. So on your left here, what we have is 1 pound weights are placed into a trash bag until it breaks. So what you see here, Kroger trash bags, 34 pounds of weights was put in before the trash bag broke, so on and so forth. Glad trash bags, 32 pounds, then 42 pounds. Hefty trash bags, we put 34 pounds of weights in before it broke. Then we took another bag of hefty, 34 pounds of weights before it broke. Tough stuff, we put 26 pounds of weight in it before it broke. 18 pounds of weight in it before it broke. So that's what each one of these is a trial of us putting weights into a trash bag before it break. The question is there evidence of a relationship between these trash bags and their average breakage? So what would be my hypothesis test? Well, my hypothesis test, my typical null is all the mu are equal. I'm going to assume all trash bags are the same until you prove me otherwise. Or another way to write that is first trash bag is going to equal the average of the second trash bag, is going to equal the trash bag, third and fourth, up until you're done. We have 4 trash bags we're comparing. That's why I'm writing mu1 to mu4. If there was only 3 trash bags, I would have done mu1 to mu3. The alternative is 1 is different. 1 average is different. Which one? That's not what this test shows, okay? This test is only to show that I can show evidence that one of them is different. I'm assuming all are equal. I'm going to show you that 1 average is different. Now, normally, I kind of brush off the assumptions. The same thing here. But I do want you to understand there are assumptions to this test. We don't talk much about the assumptions unless we're truly doing research because it's hard, like number 1, random. All right, well, I hope you have picked random bags, not bags from the same package because maybe that one package was defective. So hopefully you've done a randomness check to guarantee we have independence. Second, normality. Well, normality here, our number 2 is normality. So how do we get normality? Well, you would get normality by looking at the distributions of, strength of these individually. You would have to look at the strength of the Kroger trash bag was normally placed. The strength of a Glad trash bag was normally distributed, so on and so forth. You would have that. Do we have that here? I'm not sure. And if we really wanted to check this out and we really were worried about it, there is an advanced test one can check out called the Kruskal-Wallis test. That's only if you're really worried that you don't have normality. We can run into advanced test. So the Kruskal-Wallis is really if you're worried about normality failing. We do have an advanced test if you're really worried about normality failing. Third thing we check is we want equal variance among the groups. Again, something very hard to check, but you could check it utilizing the Levine test. There is a special test called the Levine test, again for advanced statistics, where you can check out if you do have equal variance. So in some respects, to run the ANOVA test, you have to run a hypothesis test prior to the ANOVA test, and that's the Levine test. The Levine test will check to see if you have equal variance. Once you have equal variance, then you can run the ANOVA test. So it's kind of like the ANOVA test has a pre-test to it called the Levine test. Again, if you're doing this in research, I would definitely look up the Levine test or my advanced videos in statistics and check out the ANOVA and the advanced videos. Right now, because we're in the very first level statistics, I'm going to assume we have random. We're going to assume we have normally distributed data points. And I'm going to assume the variances are pretty roughly equal. There is a lot of robustness when it comes to this test, which means if they're close to normal, we're good enough. If the variances are close enough, we're pretty good. So there's a lot of robustness. This test is really robust, as they call it, for some departures of normality and equal variance. But if you are worried about these issues, please look into either the advanced test if you have worried about normality, and or checking out the equal variance test called the Levine test. All right, so that's kind of like my quick little point on the assumptions you should check if you're going to run the ANOVA. All right, if you pass these, and let's just assume for now we passed these, then we can run the ANOVA test. So how does one run the ANOVA test? In Excel, the test is actually pretty easy. What you would do is go to Data, Data Analysis, and I'm pausing here because if you don't have the data analysis package, you should look for a video to make sure it's attached. Now that you have the data analysis package attached, you can run the single factor ANOVA. So we click OK. Input the range. Yep, here is my range of data with the titles. And I'll say labels are in the first row because I did that. You have to know what test you're running. Notice alphas here. You have to know what test you're running. Let's just assume we do the 5% alpha that is typical. If the question does want a 1% alpha or a 10% alpha, please change the alpha and run the test. Output range, I like to put it on the same page, but as I always heat in my videos, bottom to the right should be very empty. A lot of information is coming. So again, scroll in the input. Check off the labels if you did highlight labels. Make sure your alpha is correct for the test you're running. Read the question you're doing. And then click OK. And there we have it. Our ANOVA has been run for us. So what do you get in this ANOVA information? First, let me hide this because we don't need it right yet. That's the second example. Let's look at the first example. What we have here is for each group, it's going to count the number. Awesome. It's going to sum it up. It's going to find the average and the variance. So I can quickly look here and see, are the variances close? Well, I've heard rules of as long as the lowest and the maximum are not 3 times apart, you're pretty good. And for the most part, 8 and 18 are close. If you're worried about this, we can run the advanced test called the Levine test. Again, that's for advanced statistics, not this course. I'm just looking at the fact that my lowest and my highest are within triple, so we're okay. That is, if I triple this number, is within that. So I think we are pretty good for variance. Now, how do I determine if my means are all the same or means one of these is different? It's called the ANOVA test. I expect you to read the notes I have provided about the ANOVA test, what it does, and how it gets to, bottom line, this right here. The F, which lends me to these two values, the p-value and the critical value. So when I go through any hypothesis test, okay, when you go through any hypothesis test, you should have an F critical region. So what's an F critical region? Well, the F distribution is one of our first distributions which is skewed to the right. So I expect larger values out. Please understand, the F distribution is skewed right. Hence the tail to the right you see below. So in any hypothesis test, you need to have a critical region, the 2.866. Well, the 2.866, that's based on calculus. It is based on a particular amount of alpha. In this case, we let alpha be 5%. With this alpha being 5%, via calculus, I can create this threshold. This threshold says I reject H naught if I land over here, and I do not reject H naught if I land over here. So there's 2 levels of sand. If you cross this bar, the 2.866, which again is found by advanced calculus, I will reject H naught. If when I calculate my test statistic and I land over here, I don't have enough evidence to reject H naught. So this is my picture. When it comes to critical regions, I always draw my picture. In this case, a skewed right picture because it's an F distribution. An F distribution is not a T or Z. It is skewed to the right, more area to the right. So there's my critical region. Now, next thing I often teach you guys is to build your statistic. So my F statistic, as reported by Excel, is 48.108. That's my F statistic. Well, I look at my region, and I look at 48. 48 is right here. I mean, look at that. 48.108 is clearly in the rejection region. And so by the critical value approach, I now know my answer. I now know I have evidence to support that one of those averages is different. I'm not sure which one it is, but I do know one of those averages is different. See, we tested, my hypothesis was, all are equal. I now have evidence, given this rejection region and given my statistic, I now have evidence to support the fact that one of them is different. More might be different, but at least one of them is different. How do I figure out which one is different? Well, that's known as a post-hoc test, again, in future videos. We'll talk about that a little bit more in the distant. Now, some of you might say, I need to know the p-value approach. Well, the p-value approach, what happens is, again, it's skewed to the right. But now, you don't take an arbitrary critical value. You take your statistic. My statistic was 48.108. And you ask the question, how much area? What is the probability we can rerun the test and get a more extreme probability? So the p-value is the probability you can rerun the test in random and get in a more extreme sample. That's the p-value, the area more extreme. Well, that p-value, once again, is done by advanced calculus. Thankfully, ANOVA found it for us. It said the area above, so the p-value here, the area above that is extremely negligible. You look at Excel, it's extremely negligible, which means the odds of you repeating this sample is 0%, which means this, once again, is less than alpha because that's our test. If our p-value is less than alpha, we reject. Well, honestly, this p-value is less than any alpha that I can think of. My alphas I use are 1, 5, and 10%. All right, this p-value is really, really small, what does that mean? I reject H naught. So I now have two conclusions. I have the critical value conclusion, that is my sample falls in the critical region, which means I reject, and my p-value, which is, again, the area more extreme than my sample. All right, this is my sample. Green. I lost my drawing ability. There it is. Green. My sample is more extreme. All right, the p-value is, again, the probability you could be more extreme than your sample. The odds of that is almost negligible, so 0%. That is less than any alpha. Again, this would be called a triple star significant result. We now know triple star significant. That ties into the fact that you're under 1%. Triple star significant means 1%. 2-star significant would be 5%. 1-star significant would be 10%. This result is clearly triple star significant. So I reject H naught again. What does that mean? I have evidence that one of these means is different. That one of these trash bags on average has a different level of toughness. That's what I have. So I can write that down. I have evidence at a 5%, because that's what we tested. Remember in the beginning, right? We ran the ANOVA at a 5% level. I have evidence at a 5% level of significance that one of the means is different. That's all I have. I don't have any more. I can't tell you which one is different. I just know one of them is different, okay? I have evidence at a 5% level of significance that one of the means is different. And I would report all the information up here. The p-values, blah. The F statistic is in the critical region, right? You report that information in your summary. I have evidence, and this is why I have evidence. My p-value is less than alpha. My F statistic is in the critical region. Those are both supporting your evidence. If you want more, you can look at if you want to know who is different, I would run a Tukey-Kramer test. See, when you're talking about ANOVA, we're on the border of getting to some very advanced stuff. I would look at one of my advanced videos on Tukey-Kramer. I wouldn't run Tukey-Kramer in Excel. It's very tedious. I would utilize RStudio. RStudio can run all levels of ANOVA and Tukey-Kramer test real quickly. So not only could I determine that one of the means was different, I could easily find out exactly which mean was different, if not more means were different. All right? So again, this is more for advanced. I'm just saying this as a suggestion, as an advanced note. This is not part of our class, our basic level class, but if you're looking for an advanced note, I would look at the Tukey-Kramer test to identify which mean was different. Again, I assumed they were all equal. You need to give me evidence at least one is different. So given the assumptions were checked, which we checked them, we're assuming them again in our first level. If you're doing an advanced course, you would definitely run the Kruskey-Wallis if you're worried about normality. And you would run the Levine test to guarantee the equal variance. In this class, the first time around, we just assume these so we can look at the ANOVA test. So again, the ANOVA test, what it does is it gives me an F statistic, which I judge against a critical value. How does one get the critical value? Well, we use calculus and the alpha you give me. The alpha we stated was 5% in this test. Well, my statistic falls in the rejection region because either you're above the critical value or you're below it. If you're below it, you do not reject. If you're above it, you reject. And so that's why I reject my F statistic. Notice how much Excel does give me. In a simple test, my p-value is less than 5%, and that's why I reject, and I know I have one of these is different. I can also say my F statistic is way past my critical value, and that's another reason why I reject. I can look at these three key pieces and reject H naught. And that's really what I'm discussing here. But I'm really trying to put some oomph, some power behind your statements. What is the p-value? Well, the p-value is, again, the probability you can repeat the procedure randomly with different trash bags, the same companies with different trash bags, and get a more extreme result. The odds are very, very thin. So that tells me I reject because I cannot replicate this study. All right, so what do I have? Bottom line, I have evidence at a 5% because that's what I tested, though I'm saying with my p-value, I even got better results than 5%. But I have tested at the 5% level that one of these means is different. I don't know which one it is. If you want to know which trash bag is different, you can rerun, that is, you can run the Tukey-Kramer test in advanced statistics to pinpoint which one, if not more, which ones are different, which groups are compared. See, bottom line, these trash bags, maybe, and I'm just looking at the averages here, that's kind of a cheating point. I can look at these averages and I'm thinking Kroger, Glad, and Hefty are very similar. I think Tough Stuff is not the same. So I'm wondering when I run my Tukey-Kramer in advanced programs like RStudio, it's going to say Kroger, Glad, and Hefty. Yeah, they're very similar. Tough Stuff is the one different. In fact, you can think outside the box right now and think, how could I do that right now? How could I test that Kroger, Glad, and Hefty were all the same, but not Tough Stuff? I'm pausing for, effect to give you a chance to think about it. You're right. The answer is, why don't you run an ANOVA just on Kroger, Glad, and Hefty? That is, let me do that. Let me do a data analysis dump. But this time, I don't want all the data. Let me run it on the three I believe are equal. Based on this prior ANOVA, it looks like the averages of these three are the same, but this is really out of whack. Tough stuff is. So I'm just making a huge leap of faith. This is called a Posthoc test. You're trying out to see if you can eliminate one of the options quickly. So now, of course, I do need an area where bottom and lower is empty. So right here, boom, run my test. And I check out my new ANOVA results. My new ANOVA results state my F value is 0.32. It does not come close to the F critical value, so I would not reject. And also my P value. The chances you can rerun this test would be 72%, which means, wow, you can rerun this test with pretty high odds, which means my p-value is not special, which means I would not reject. Which tells me, in this case, if I'm looking at this test, if I was testing just these three trash bags, I would not have evidence to reject, and I would assume they're all the same right now. Again, according to this ANOVA, which is only on Kroger, Glad, and Hefty, I'm looking at this test and going, wow, this F statistic does not beat the critical value, which means I do not reject. This p-value does not go under any alpha, 1, 5, or 10%, which means I do not reject. What does it mean to not reject? It means I believe these averages were all equal. So I do not reject these being different. But think about this. This big test said one of these four was different. I ran a sub-test. I said these three are not different. Think of that. We have all four I ran. One of them was different. I ran these three, and none of them were different. Means tough stuff must be the one different. I did not need to run the Tukey-Kramer result in this case. I just used my intelligence factor that I looked at the averages and one looked really different, and that's why it's pointing to the fact that, yep, definitely tough stuff is different. And that's how I run an ANOVA test. Now, all the details with it, I would expect you to read up on these. All right, there's many videos on what do these represent. I mean, how does one build an F statistic? Well, an F statistic is built on the ratio of two averages, average variations. That's what these two numbers are. If you divide these two, you get the F statistic. These two are the average squared variations, okay? So the F statistic is a ratio of variations. We're looking at the variations between the groups and the variation within the groups. Look at the titles here. The ratio of these, if it's too big, if the ratio of the variance is too big, then the F statistic, which is the ratio of the variances, would be too big. I expect this, if there is no difference in how these groups are broken out, all right, if there's really no difference between the groups, this ratio would be close to 1. I'd expect these two numbers to be relatively close to each other. Look down below here. Look at these two numbers. These two numbers are pretty close to each other, and that's why the ratio was pretty small, and that's why I did not reject. Up here, this is a pretty big difference here, all right? That is a 48 times difference, and that's why we're rejecting. Now, where do these come from? These come from degrees of freedom and sum of squares arguments. You should read up, if you really truly want to know ANOVA, you should read up on how these two divided turn into this, these two divided turn into this. But where do these two numbers come from? You have to understand how each thing is built to truly understand an F test, okay? That is an ANOVA test. I can give you a summary right now, and I did. The summary is Excel pumps out the three things I need for any hypothesis test. I have the F statistic, which beats the critical value, and that's why I reject. I have the p-value, which is based on the F statistic, and my p-value is less than any alpha. That's why I do reject H naught. And since I reject H0, I go look and see what H1 was. And in this case, H1 was at least one of the average is different. And that's what I get to report. I got lucky and I was able to isolate the one average that was different quickly using just my street smarts. If you couldn't isolate it because you had a lot of groups, then what you would do is run the Tukey-Kramer to pick off the ones that were different. Because a couple could have been different. You could have isolated that maybe Tough Stuff and Heavy were the different. They were grouped together in a lower strength, and Kroger and Glad were higher strength. Well, I mean, we haven't ruled that out. To be honest, I haven't ruled that out yet. Tukey-Kramer will run through all options. One is different, two are different, so on and so forth. It'll run through all options. It's a very advanced test, and it's really cool to see. So I'd almost run the Tukey-Kramer myself in our studio to make sure that I didn't miss any other differences. Though with this ANOVA here lends me to the point that I don't think I'm missing anything else. This ANOVA here says all three are relatively the same with these numbers right here. All right, running this ANOVA really tells me they're roughly the same, so I don't think I'm going to miss anything in the Tukey-Kramer, but you can run it just to learn about it in the advanced classes. I do want you to understand that I have not discussed these. All right, these details are important, and you should read about how the 48 comes from the ratio of two variances. The variances of between groups and the variances within groups. What do they represent? Well, what they represent is the ratio of these two numbers. If you divide this by this, you get this. If you divide this by this, you get this. But what is a variance? A variance is a sum of squared divided by a degrees of freedom. That's really what a variance is. If you look at the definition of variance, it's a sum of squares divided by degrees of freedom. All right? So where do these numbers come from? Well, the degrees of freedom is easy to explain. A degrees of freedom for between groups, well, if there are 4 groups, n minus 1 would be 3. All right? There are 4 groups, so n minus 1 would be 3. The total degrees of freedom makes sense because I have 40 numbers. Okay, I have 40 numbers, and again, n minus 1 would be 39. So hence, the degrees of freedom within is just the enough degrees of freedom to get to the total. You see, these two numbers have to add to this. That's kind of our check. These two numbers have to add to this. So if we have 3 groups and n minus 1, if we have 4 groups and n minus 1 is 3, that's where that number comes from. And if we have 40 total values, look at the chart, 40 total values, then n minus 1 degrees of freedom is 39, and hence 39 minus 3 would be 36, and that's how I got that number. How do you get these sum of squares? You have to understand what you're analyzing. And what we're analyzing here is 2 different things. We're going to find the average of all of this. We're going to find the average of all of these numbers. And we're going to take each number away from that grand average and sum them up squared. And that's what this is. That is, if I take a look at each one of these numbers minus the grand mean of all these, square it and add them up, you get this. That creates my numerator. Then if you look at the space between, that is within the groups, all right, you look at the space within the groups. What you're going to do is, if you look at how far this number is away from the average of the group, this number is away from the average of the group. So this is the average of Kroger. So I take this number minus this number minus this, and they're all squared, by the way. That's why it says sum of squares. You take 34 minus 35.4 squared, add it to 30 minus 35.4 squared, added together. And you continue that down for each one of them, because then you would move on to Glad. So Glad would be 32 minus 36.3 squared. If you continue that analysis, you would get this sum within the groups. These 2 comparisons is what you're looking at when you divide out by the degrees of freedom to create the variances, the average squared variance. These 2 averages, and the mean, MS is just another word for average, mean squared variance, all right, you're looking at this ratio to be close to 1. Because it doesn't matter if I look at all these numbers randomly against the total average, or each one individually within the average. if there is no difference between the trash bags, I can flip-flop how I measure average, and this ratio would be close to 1. The more closer to 1, the closer this number is to 1, the more I believe that they're all the same. And that's really the idea. The closer this number is to 1, the ratio is to 1, the F statistic here, the ratio of these two, the more I believe that the averages are all the same. But again, once again, bottom line, this number was well past 1, and that's why I rejected. All right, guys, let's pause this video in a second. Sorry, what I want to do is, where's the information hiding? There it is. Unhide it. I want you to try example 2 now. You try it. We'll be back to see how you did. All right, we're back after my quick pause. So what do we got here? A study is performed on if watching too many medical dramas can increase concern about medical health. So we group people based on their watching habits. Little on medical dramas, moderate, and substantial. And then we asked a question if they had any health concerns. And this is what these people reported. So notice there's 10 people in each category, randomly placed. So we got the random. How do I have normal? I'm going to assume a normal in this case, but you should substantiate that. You should run box plots and check for normality. Last but not least, equal variance. If I'm worried about equal variance, I'll run the Levine test. If I'm doing research, I would run all these things to ensure that I have the assumptions needed to run ANOVA. Again, that's the second layer when you're doing research. Right now, I just want to run the ANOVA test. Let's go back to here in our document. So again, any test, any hypothesis test, I start with the H-naught. My H-naught is I believe the 3 groups have the same average. H1 is someone is different, at least someone. Someone is different. We're not sure which average is different, but somebody is different. Normally now you let down your alpha. What alpha do you want to use? 1, 5, or 10%? Which one do you want to use? You would dictate the test to me. Which alpha do you want to use? And then from there, I do have to run my assumptions. I'm going to skip over them again because this is an intro class into building ANOVA. Please watch future videos to see how you would check. Look at my advanced stats playlist for those if you'd like to see how you run them. All right, so what do we got here? So I want to run ANOVA. To run ANOVA, you go data, data analysis, ANOVA single factor. You highlight your data with titles. I like to have titles in there now. If you don't have titles, don't click that. Alpha is 5% or whatever number you choose, 1, 5, or 10. Put it in there, please. Output range, like I've heated many times in my videos, please, oh please, pick a spot bottom right. It's empty. Done. Beautiful. So this is my ANOVA on this data. Allow me to hide the previous question. Right click, hide, and we can look at example 2 together. So in example 2, first thing I notice is the averages are pretty similar. So I should not, be too concerned. But as I look at my quick answers, I can see I'm in a gray area. So we need to talk about that. Variances look pretty close. Again, if I worried about the variance, I could run the Levine test. I always look at, as long as my low and high are not 3 times apart, I'm pretty good. If they're more than 3 times apart, I probably should run the Levine test. So, all right, what do we got here? The ANOVA. Well, it speaks for itself. I mean, really, it is right here, all 3 of these. These 3 numbers are essential. My critical value is 335 for 5% level. My F statistic is 425. I barely beat the critical value, but I do beat it, which means I will reject. My p-value is under 5%, so I would reject. So I do know I reject, and it's as simple as that, guys. We're done. I'm going to look at this a little deeper because, I want to help you guys out, learn a little bit more. So again, first of all, the critical region. I always draw a picture, and I ask students to always draw a picture to understand the F distribution is shifted to the right. It's skewed to the right. It's one of the first times you see that. The critical value is a bar set down based on alpha, based on what measurement you want for rejecting. And that's really what you've done. You've created the reject H-naught region, and you've created the do not reject H naught region. Now it's based on your data. Now what you do is you collect your data and you collect your F statistic. You collect your data and you calculate out your F statistic, which happens to be 4.25 here. That's your F statistic. And I notice my F statistic is in the rejection region. And that's it. Done. My F statistic is in the rejection region. It's crossed the 5% threshold for which I reject. And we're done. To add a check to that level, you can run the p-value. The p-value and the F statistic, the p-value in the critical region should state the same thing. They should say the same thing. So my F statistic comes down here, makes a bar. I want to know the area outside that bar. The area outside that bar is called the p-value. Well, that is advanced calculus, so thank you, Excel, for doing the advanced calculus, and that's 0.025, better known as 2.5%. This, once again, lines up to the fact that alpha, right, this is less than alpha, and that's why I reject. So my bottom line summary is I do reject, all right? That's my bottom line answer. I do reject, and I have evidence to support that one of these averages is different. One of these groups clearly has a different average than the rest. Which one is it? We'd have to do the Tukey-Kramer to figure it out, all right? But right now, I know one of these averages is different. Please notice something. This guy is double star different. That means it's less than 5%. If I change this to 1%, we're not going to get the same conclusion. If I change this to 1%, notice that. If I change this to 1%, my p-value is no longer under it. That is, if I change alpha. Note, if we change alpha to 1%, we do not reject H naught. This means our p-value is sensitive to alpha, all right? Our p-value is sensitive to alpha. So if we change alpha, which we shouldn't, you shouldn't just flip-flop in the middle of the test. But if we change alpha to 1%, we would not reject. That's why some people like the p-value, because they can report their percent and say, this is how special I am, 2.5%. And that is 2-star significant. That's all you need to say. My p-value is 2.5% and it's 2-star significant, which means it's under 5%. If we're doing a critical region test, you have to tell me the critical region ahead of time. At a 5% level, you're rejecting. If we rerun the ANOVA at a 1% level, we would not reject. And that's very important to note. All right, you need to set down your alpha carefully to decide if you reject or not. And that comes clear in my p-value right here. Again, my p-value is underneath 5%, and that's why I do reject. But my p-value is greater than 5%, so that's why I call it sensitive. It is sensitive to the alpha value, that p-value is. Not all are. Look at the previous question. They were not sensitive. This one is sensitive to the alpha value. Bottom line, my alpha was 5%, so I will reject H naught at LOS 5%. At a 5% level significance, I will reject. What does that mean? I have evidence that at least one mean is different. That's all I can report. According to my evidence in the ANOVA, at least one is different. You would want to run the Tukey-Kramer to figure out exactly which ones are different, which two are the same, maybe all three are different. See, we're in the scenario here when we have three groups. All three could be different. Or maybe little is different than moderate substantial. Or substantial is different than moderate and little. All right, you have to run a Tukey-Kramer here to check out which one's different. All right, I can tell you at least one is different according to my ANOVA. That's what I want you to understand. I can tell you which one's different. That one is different. I can't tell you which one it is. It's kind of like a great story, right? End of chapter 1. Woohoo! Somebody is different. Dun, dun, dun. Stay tuned for part 2, and we'll find out which one is different. Or maybe all three are different. I don't know from this information. And look at these averages. Oh man, there's too close to tell. That's why I'm hedging. I don't know, according to this, which ones are different. So I'd run the Tukey-Kramer to be clear. And again, the Tukey-Kramer, you can look at my advanced videos to see it. It's very easy to run in RStudio. This is the point where I start saying to my students, stop looking at Excel, go into RStudio or advanced programs, because they run these advanced things easily, these additional things easily. I like RStudio because it's free. That's why I keep mentioning it. Now, we're done. But as a good professor, I want to state, where did the F value come from? The F value came from because you're measuring the ratio of these two numbers. All right, I want to make that clear. The F statistic is becoming from these two ratios. And this ratio was more than the critical value. Where does the critical value come from? You really got to do advanced calculus before you can even understand the F critical value truly. And the same thing with the p-value. They are coming from advanced calculus, and without Calc 3, Calc 2, you really aren't going to have a handle on them. So I leave that to you in your grad studies to understand those. So remember, the focus of this video is your first time around seeing ANOVA. And again, a single factor ANOVA. There are many other levels of ANOVA. Check out my future videos on ANOVAs, blocking, randomizing. There's other options. I'm just looking at how does one create this table? Well, these two numbers divided gives you that. But what are these numbers? Well, the mean squared between, that's nothing more than the division of a sum of squares over degrees of freedom. Because that's really what variance is. Variance, mean squares, is another word for not mean squared within. That is a ratio of sum of squares divided by degrees of freedom. So that's how you get them. Now you really got to understand what mean squared means. A mean squared, what it is a good old definition of variance. That's why when I talk about the F distribution, this is a ratio of variances, because these two numbers are variances, all right? These two numbers are variances. The ratio of variances is the F distribution. What is a variance? A variance is really just a sum of squares divided by degrees of freedom. Why is the degrees of freedom here 2? Because you're looking at between groups. Well, if you have 3 groups, n minus 1 would be 2. If you look at total degrees of freedom, well, if there are 30 numbers here, n minus 1 is 29. And again, the basic math of why this is 27 is because the degrees of freedom of between and within have to add up to total. So if I know n minus 1 for total is 29, and n minus 1 for between is 2, then I know by basic algebra 2 plus 27 must be 29. And that's why I got that number. Where did the sum of squares come from? Well, this is a deeper topic. All right. The sum of squares between, all right, to do the sum of squares between, what you first need the grand mean. The grand mean. What the grand mean is the average of all of these items, the average of, nice, got cap locks on, the average of all of these items, regardless of what group they're in. And that's really what I'm studying first, is I want to know, regardless of the groups, what would be the spread? And that's what SSB measures, is what is the spread regardless of whatever group you're in. And so what you would do, you honestly would take each number, each and every number, take off the grand mean. Each and every number mean squared. That's what the SS stands for, sum of squares. All right? Plus, and you would do it no matter what column you're in. You take each and every number off from the grand poobah mean squared. And you would continue this all the way through all 30 numbers. You would continue for all 30. And that's when you would get the number up there, 31.667. You would get that if you continue that formula for all 30. Due to time, I'm not going to do that. Of course, SS within, the sum of squares within, which is what you divide degrees of freedom by to get the mean squares within. The sum of squares within here, how does one get that number? Well, this is the averages compared to the group. See, this is the sum of squares compared to no matter what group you're in. This is depending on the group you're in. And the ratio of these, if it matters what group you're in, the ratio is going to be far apart. If it doesn't matter the group you're in, these ratios would be close. And that's the idea. If the ratios are close because it matters what group you're in, if it matters what group you're in, the ratios will be far apart. If the ratios are close, it doesn't matter what group you're in. So here, what you would do here, you got to be very careful. Here, you take each individual item minus the average of the group they're in, and that's very important, and then squared. Plus, and so that would be different here because this number, that's in the moderate group, and the average of that group was 5. And then you would square that, plus, and then you would take this guy, take away the average of that group it's in, squared. And by the way, you need to continue this. I know I wrote the formula wrong. I understand that. That should be a squared. I saw that. Just had to get to it. You must continue this, by the way, through every element. You don't just stop. You continue this through every element. Minus, back to the 4. Not sure why it's not clicking. There we go. Square it again. And this continues. All continue for all 30. And you will get, I promise you, you will get 100.5. So again, the basic understanding of what an ANOVA does is it compares each element to the grand mean. So it says regardless of what group you're in, let's see how far apart you are. And that's what this variance is, the spread factor is. Then it says, all right, you're grouped for a reason. Let's measure the variance inside the groups. Let's measure the variance inside the group, which I did here. And that's this number. If there's really no difference in the group you're in, then this ratio should be close to 1. If there is a difference, depending on the group, then this ratio will be farther away from 1 than acceptable. Again, this is the acceptable limit at 5%. We are clearly farther away than acceptable, and that's why we're rejecting. All right, guys, thank you for watching my video. Stay tuned for others.